Hi guys, welcome back. So we are still busy with the concept of investigating triangles. So let's just quickly recap on what we've spoken about in our first segment. We looked at the theorem of Pythagoras, but because only when we knew that our triangle was a right-angled triangle. So the very first thing that we look at is if the triangle is right-angled or not. And then only then can we talk about the theorem of Pythagoras. We looked at the names of our sides in relation to the angle that they are adjacent to, opposite to, or the longest side of the triangle. But remember, the longest side must only be long and also opposite 90 degrees. Then can I call it a hypotenuse side, not only long, because remember some triangles, they do have longer sides but they not having a 90-degree angle. So just make sure that it is the longest side and also it is opposite 90 degrees in terms of a right angle triangle. We also looked at the concept of how can I find sides, right, given maybe one side or given two sides. Now we're going to talk about the concept of ratios to do that, because that's the main thing that we're going to be using in trigonometry to try and find an unknown side given one side and an angle maybe, or given two other sides and we want to find the other side given all of that. So that's what we're going to talk about. So now the main thing that we're looking at is the concept of ratios of sides and angles. Now, with a ratio is the comparison of two quantities of the same unit, right? So I cannot compare rands and compare it to kilograms. That will not make sense, right? So the ratio that I will want, if I want a ratio of rands is to something, it will have to be rands is to rands, kgs is to kgs, grams is to grams. So it must be two quantities that have the same unit. In trigonometry, ratios are given as common fractions or decimal fractions. So that means it can be given as 2 over 3, that's a common fraction, or it can be given as 0.5, which we know is the same as 1 over 2. So it can always be given as either a common fraction or a decimal fraction, depending on what the instruction is at the time. Remember, at times the instruction says round off to 2 decimal places or leave your answer in the simplest fraction form. You just need to look at what is the instruction at the time. Also, have you now thought about if there is a relationship between the sides and the angles of a right-angled triangle, right? So firstly, we looked at the relationship between sides, which we said was the theorem of Pythagoras. But now, is there a relationship between those sides and the angles of a right-angled triangle? What do you think about that? I just need you to be thinking about that as we are busy with what we're going to do, because that's the big idea that we are trying to answer with this investigation. Now, consider the triangle below, right? So you can see that I have the angle 30. I know what side A is. I know what side C is. Remember, the reason why it's A, C, and B, it's because it is a side opposite vertex B, vertex A, vertex C. So we name it according to that. The big question will be, what will then be the ratio of A over C? So that simply means I just need to substitute the value of A, which is 1. I divide it by the value of C, which is 2. So this is the same as 0.5, right? Common fraction, decimal fraction. Remember, that's what I said a ratio can be given as. Also, if maybe we look at a second similar triangle. Now, quickly, let's just do a quick recap of what similar triangles are about. Remember, similar triangles are when sides are in proportion meaning for us to get this side from this triangle to the other triangle, we will be multiplying by the same value or dividing by the same value to get one of the other sides from one more triangle. You see? So if things are in proportion with one another, meaning they don't necessarily need to be equal, as long as maybe they have the same angles, but the sides can be bigger. We call them similar shapes in just general. But in terms of triangles, it's when they have the same angles, but different sides in terms of lengths. And the lengths are bigger, one is smaller. As you saw, the first one had a 1 and a 2. With this one, you will see it has a 2 and probably a 4. And then the next one will also be a similar one, but the angle will remain constant throughout. So we'll look at that, please. Now, with this one, our ratio, which is still A over C, so we're not looking at what B is for now. We're only focusing on side A and side C. So A over C will be 2 over 4, which is the same as 1 over 2, which is the same as 0.5. So far, if we look at the previous slide, we saw that our ratio was 1 over 2. Even here, our ratio is still 1 over 2. Why? Because these are similar triangles and not just any triangles. Now, the third similar triangle below, now it has 3 and 6. Let's look at the ratio. If it's the same, then bravo, we are still talking about similar triangles. So the ratio will be 3 over 6, which is the same as 1 over 2, which is the same as 0.5. So you see, we're still talking about similar triangles. The fourth similar triangle, I just have my label A inside the triangle, but it is just really for this side. I just wanted it to be clear, hence I put it inside there. So please don't be confused and think it has to do with the interior of the triangle. No. Now here, our ratio, again, we're still looking at ratio, will be 4 over 8, which is definitely 1 over 2, which is still the same as 0.5. Now, what exactly do you know about this? We saw that our ratio is 1 over 2 for A over C. It was 1 over 2 for A over C for the second triangle. For the third triangle, it was also 1 over 2. For the fourth triangle, it was also 1 over 2. Why? Because they were similar triangles and the angle was the same throughout, which really makes them similar. Now, the opposite of this, or the reverse operation, which we then call the reciprocal, right? We call this the reciprocal. It's when we tip and times our numerator and our denominator. So the ratio of C over A will be 2 over 1, which is just 2, which is just 2, 2, and 2 there. So you can see that the ratio is the same 1. The reciprocal is also the same, that's number 2. Now, what is it that we can conclude from seeing the ratio of AC and CA? We can see that they are reciprocals of one another. If we take one as the original ratio, the other one will be a reciprocal. I know you've learned a reciprocal at a very early age in terms of your grades and your maths. Now, in our conclusion, is our conclusion for the ratio A is to C true for the other ratios, right? What do I mean when I say for the other ratios? If now I'm comparing B and C, and I'm comparing C and B, also comparing A and B, what will happen? Will it still be the same ratio or not? So that's one thing that we will need to be able to answer, because remember, for you to draw a conclusion, it means that it must be general for everything that you are doing, because we are trying to have a general concept, remember, a model that we can use for all the triangles, given that it is a right-angled triangle. Now, I want you to please complete this table for me, and just look at what will be the ratio of A over C if I know that the side B is root of 3. By the way, I got a root of 3 using the theorem of Pythagoras. So let's just quickly go back to this. Remember that if I look at this, right, so my theorem of Pythagoras will then be B squared will actually be C squared minus A squared. And C squared will then be 16 minus the 2 squared will be 4, and this will give me 12, and that's B squared. So if I want to find just B, it will then give me square root of 12, which is the same as square root of 4 multiplied by square root of 3, which is 2 root of 3. So what does this mean? Remember, when my side A is 2 and my side C is 4, my B will then be 2 root of 3. But I'm sure you are familiar with using the theorem of Pythagoras, because we did it as well at an early age in terms of our schooling career. So I want you to take some time and fill this table in. After filling this one in, you also need to then take some time and fill the second one in. Remember, here it's when we look at the reciprocals, right, of what the ratios are, because we looked at the first ones as our original ratios. But now what you need to then look at, what is the conclusion that you can make about the 6 ratios when the angle is 30 degrees but the size of the triangles are different? Now, what am I talking about? The angles must remain constant throughout, but the sides can be bigger, others can be smaller, as long as the angles are the same. What deduction can we make about the 2 ratios, A over B and B over A over C, C over A over B over C, and C over B? What is it that you can actually make in terms of the conclusion between the two? That's the main thing that is going to assist us in seeing the bigger picture of what we are trying to do. So make sure that you complete those tables and look at what exactly can we say about those two comparisons in terms of 3, because it's 3 normal ratios and 3 reciprocals. So you can see that if you were to complete this, this is what it will look like. A over C will be 1 over 2 for all of them. B over C will be root 3 over 2 for all of them. And then A over C will be 1 over root 3. So that's not supposed to be A over C. It's actually supposed to be A over B. Apologies on that. And then you can also see that with the second table that I said you need to complete, it's just a reciprocal of what we have, right? So it's tip and times. The numerator swaps with the denominator. Hence, it's 2 over 1, 2 over root 3, and root 3 over 1. Now, what do we predict if the acute angle now is 60 degrees? What do you think? Also, if it's 45 degrees, what do you think? I want you to think about that. Remember, we've only been looking at the acute angle being 30 degrees. Now I want you to look at what happens if it's 60 degrees. What happens if it's 45 degrees? Will the same deductions that we made still hold, or will they be different, or will be there any variety that we're going to look at based on those deductions and those tables that I said you must fill in? You can draw them again with the same values and see what will happen in that particular context. Now, will the ratio remain constant for all similar triangles? That's the big thing that you want to look at. And then also, will the ratio, if you were to tip and times it, will it be the same as the original ratio? That's the big thing that I want you to do now. So as we go into an ad break, please try to investigate that. Draw 2-3 tables, fill them in, look at if the angle is 45 degrees, if the angle is 60 degrees. Remember though that the angles in a triangle, they must all add up to 180 degrees. So you can't have 60 and 60. It wouldn't make sense. So it will be 60 and 30. So it will still be in the same triangle as the one that we've been using. But if it's now 45 degrees for it to be 90, you know it's going to be 45 and 45. Just compare that and look at it. And then we'll be back. We'll talk about it some more just after the ad break.